In this session, we're going to look at the three basic gates that form the foundation of every digital logic circuit. There are three ways that we can represent digital logic: a circuit diagram, a Boolean equation, or a truth table. The circuit diagram uses electrical symbols to represent each of the gates. Wires join our inputs to our gates, gates to other gates, or gates to outputs. These circuits need to be carefully designed to produce the desired results. The second way to represent our logic is using a Boolean equation. Like a math equation, we have a result, y, and a combination of our inputs or variables that specify exactly how y is going to behave. The last way is our truth table. We have our inputs, A, B, and C, and then we have a column that defines our outputs. So here we can see every possible combination of our inputs, and we can see how our output y is going to behave for each of those inputs. In this session, we're going to look at the electrical symbols, Boolean equations, and truth tables for the three basic gates, and by the end of this week's class, you'll be able to design and build simple digital circuits. Before we can talk about the gates themselves, we have to understand a little bit about digital systems, ones that are either on or off. There's no sort of or approximately in a digital system. Individual inputs are either on or off, which, depending on the system logic, produces an output that's either on or off. There are three common ways to represent these on and off states when working with logic. On is typically represented by a 1, a high, or a true. And off is represented by a 0, a low, or a false. In this session, we'll be using 1s and 0s to represent the highs and lows in our circuits. The first of the basic gates is an inverter, or a NOT gate. As its name implies, the output from this gate is the opposite or inverse of its input. That means if the input is high, the output will be low. If the input's low, the output will be high. The electrical symbol for the inverter is a triangle with a bubble on the tip. We're going to see that bubble a lot. It means an inversion, so we're going to see it as we use other gates as well. An inverter has only one input, in this case labeled A, feeds into the inverter, and then on the output we have one output, in this case called X. Our Boolean equation for this always shows the output on the left-hand side. Here we're going to have X equals A, which is our input, and an overbar, which means inverted. So here we would say X is equal to A naught. Our truth table is used to define the behavior. We know that the output's going to be high when the input's low, and it's going to be low when the input's high. So in our first case, we have our input low. That means our output's going to be high. Second row, we have our input high, which means our output is going to be low. So we now have a complete truth table that defines the behavior of our inverter. The second gate is an OR gate. As its name implies, the output for this gate is active when any of the inputs are true. So that's the key thing to remember, any of the inputs. The electrical symbol for the OR gate is a rounded triangle. So we've got a rounded input edge and rounded side edges. We have two inputs, A and B, and one input, X. Our Boolean equation has the output on the left, so X is equal to A or B. So the OR operator is a plus sign. We have to be careful not to confuse that with addition, so we don't say A plus B, we say A or B. Our truth table here has to account for our two inputs, A and B, and all four possible combinations of inputs. So when they're both low, when A is low and B is high, when A is high, B is low, and finally when they're both high. Our output is in this column here, labeled X, and we know that that output is going to be high when any of the inputs are high. So if we look at the second row, we have B high here, which means the output of the OR gate will be high. The third row, A is high, so our output will be high. And finally, in the last row, both of them are high, so our output will be high. In the first row, neither of them are high, means our output is going to be 0. The last of our basic gates is an AND gate. As its name implies, the output is only active when all of its inputs are true. The electrical symbol for an AND gate is a rounded rectangle, so we've got the nose rounded. Here we have two inputs, A and B, one input, X. Our equation has X on the left-hand side. It's equal to A and B. So here we can either use a dot like we would in multiplication, or we can omit that like we would in multiplication. Again, it's important to remember that we say A and B, not A times B. Our truth table has to have all four combinations of our inputs, A and B. So we've got 0, 0, 0, 1, 1, 0, and 1, 1. And our output is going to be defined in our X column. And here we need all our inputs to be high in order for the output to be high. We only have one case that does that, right down at the bottom. So that's going to be high. All the others are going to be low. So in summary, we have three basic gates: an inverter, an OR gate, and an AND gate. Our inverter is A0. Our OR gate would be written A or B, and our AND gate would be written X is equal to A and B in either of these two forms.